Hi everybody, I will briefly present our paper. Hiphop.js is a JavaScript DSL dedicated to aid the writing of web applications that involve both asynchronous communications and complex reactive event handling. It extends the single-threaded atomic execution model of JavaScript with deterministic synchronous concurrency and communication, plus preemption structures that control very finely the life and death of their body in an event-driven way. Their conjunction makes programs simpler and more modular than with plain JavaScript, as we show in examples. Hiphop.js borrowed its core semantics and implementation techniques from the STRL synchronous language. It is compiled into plain JavaScript that can be combined with any other JavaScript code in unmodified execution environments.
Fully homomorphic encryption, or FHE, allows computation on encrypted data, thereby enabling offloading both storage and computation of private or sensitive data to public clouds. And the trust model is very simple. As long as one keeps the secret key, there's no need to trust the hardware or software like Intel or Microsoft. However, developing FHE applications is very hard because it requires choosing the encryption parameters and it requires the computation to obey certain cryptographic constraints. Both the parameters and the constraints affect correctness, security, and performance. In this work, we introduce a language and compiler called EVA. The language provides encrypted vector arithmetic instructions that hides the cryptographic details from the programmer, and the compiler automatically generates optimized FHE programs that can run on multi-core CPUs using FHE libraries like C. EVA can also act as a target for domain-specific compilers. To know more about our work, I invite you to our talk on June 19th at 2:40.
When we want to do arithmetic on the reals, we usually use machine floating point. That has the advantage that it's really fast and precision is usually good enough. On the other hand, results are sometimes surprising, especially to non-experts working on mathematical problems. For example, two popular web browsers agree that when we compose a function with its inverse and compute tangent of arctangent of 10 to the 20th, the correct answer is about 1.6 times 10 to the 16th. And there are many more examples like this. There are known solutions to this, but they usually come at the cost that equality is no longer decidable, which means that, for example, 1 divided by 0 will end up failing to terminate. We'll describe an approach that always preserves expected mathematical properties and can produce arbitrarily accurate approximations, as you see here, but that also commonly provides decidable equality, as you see here.
Several recent papers have sought to combine the high-level parallelism abstraction of futures with the real-world demands of concurrent programming by allowing futures to be assigned priorities. These papers have developed cost models for responsiveness, scheduling mechanisms that respect priority, and type systems that statically prevent priority inversions. All of this work, however, assumes that programs are purely functional. A problem arises in particular when future handles may be stored in global state. In order to statically prevent priority inversions in this setting, while still allowing interesting programs, we must extend the cost models to include additional edges that capture happens-before relations on reads and writes that may manifest at runtime in order to track future handles through the program. Our paper presents the extended cost model and a type system that provably rules out priority inversions. We have implemented these ideas, including enforcement of the type system, in a new dialect of Silk, a C++-based parallel language, and evaluate its performance to show that futures can be used for performant concurrent programming.